this requires choosing a formalism for our string theory, which is not the ordinary RNS formalism. So you may start complaining, do you really have to inflict on us this pain of learning a new formalism? I will try to convince you that this is the least pain I have to inflict on you. Other possibilities would be more difficult. And then we will get to a point where we have a guess for this question mark, but at that point will only be a
question mark is the bulk theory.
Yeah, exactly. What is there a string theory which reproduces this formula, which is a formula from the field theory side, and that I can dare to claim dual is quantum theory.
The CFT you described to us so far, was it, should I think of it as a boundary CFT, or is it a
downstairs here? No,
one you described
is a field theory formula.
Boundary field theory.
I don't want to say conformal because conformal group is broken.
But still,
I can say boundary.
It is a boundary CFT.
It's a boundary CFT, but the question,
maybe
the question is, can I formulate a string theory which derives the same formula from the bulk? Okay. Okay, then I will propose some candidate here, but I want to convince that there is some evidence which is in terms of computations, not just words. So I will show you that how we can compute the string partition function. So this is a fancy way to encapsulate the spectrum and the energy levels. And I will show that this won't be scary because, again, we will treat everything in terms of free fields. So we are doing some free field path integral. So it's like going to the first days of QFT, where you show how the path integral can be done for free fields. And we will recover this square root in the end by integrating the path integral over these free fields. And at the end, I will tell you that, okay, there are still many things that you don't understand of the whole picture, but at least this level we will achieve, and I will ask you questions.
Was the ADS cross sphere cross T4 historically done in this manner by people like Kutasov and Seibek long ago?
So, okay, so ADS 3 cross S3 cross T4 has a 30 years history.
30 years.
Yeah, from the 90s already. Okay, so it's very old subject, and certainly the authors you mentioned played a prominent role. But more recently, this tensionless limit has been explored mainly by Gaberdine, Gopakumar, and Eberhard. These are the key authors. There are many others, me included in some minor results. But this understanding that when the tension is very small, the duality becomes exact, meaning that you can match all observables, not just the protected ones, is a relatively more recent result, something like 2018.
I would be very excited if higher spin theories enter, but that's another story.
Yeah, and we can discuss later.
Yeah, go ahead.
Okay, so questions? Good, so if no more questions, I can start with the first point. So how this tensionless string is formulated. So I'm talking about this line here, okay? I'm not yet at what the deformation should be. So this is just a way to present with you what we are going to deform. And so how do I define a string theory? One way is providing you a conformal field theory on the worldsheet with zero central charge, right? So for example, when we are in flat space, we have 10 free bosons, 10 free fermions, and our ghosts that the total central charge is zero, okay? This is another string theory that has a different field content. So we will not have 10 free bosons and 10 free fermions and ghosts, different field content, but still we will have total central charge zero. So it's the same logic. So this is the tensionless ADS3 string. And now I describe the field content. So we have one commuting beta gamma system. By this, I mean two free fields that have dimension 1 and 0. And that when they are brought close by, they behave according to this OP. Okay, but they are free. They are free. And then we have two anti-commuting, so Grassmann odd, BC systems, by which I mean fields with conformal dimension, again, 1 and 0, but this time they are anti-commuting. And they have two copies, so I runs over 1 and 2. And again, the OP is relatively simple. Right? And I have a topologically twisted form. So this, what I mean by this, so T4 I mean for free bosons and for free fermions. Topologically twisted means that I have a peculiar choice of what my stress tensor is. So I mean that the stress tensor will be what you're used to, what you would write for the stress tensor for free fermions and for free bosons, but I twist it by the derivative of some Cartan. So fields will take strange conformal dimensions because to what we are used to, because they will also acquire some contribution from a U1 current. Okay, and then I have some sigma free boson. This is familiar if you study bosonic string theory because it's the one that has central charge minus 26. So it's the only ghost you have in bosonic string theory. And then I have another one which is more peculiar and probably is less frequent to encounter. And this is some free boson with background charge so that it accounts for central charge plus 28. Okay. And now if we do the counting of the central charge, this beta gamma system has central charge plus 2. The BC systems are 2 copies, and each has central charge minus 2. The T4, we would say, has central charge 4 plus 2. But since it's twisted, the fact is that the fourth order pole also gets a contribution from this. So in the end, there is no fourth order pole in the OP of the stress tensor with itself. So this is central charge 0. And this we already said. So if you do the sum, indeed, it has central charge 0.
You've given up supersymmetry. No supersymmetry.
No, this is n equal to 4 supersymmetric in the end, right?
Oh.
Because I'm describing this line on top.
Of course, of course.
So there is
But
supersymmetry.
here I could
Now,
not tell.
I agree. So the point you can make is, fine, you gave us just a bunch of fields that adds up to 0, but there are a zillion possibilities.
Exactly.
What does make this special? So this is not the way it was formulated, but what makes this choice special is that in terms of this field content, in particular, in terms of this portion here, this describes ADS3 cross S3, and you can ask why, because it doesn't look so, because there exists, so if you consider the superalgebra PSU112, so this is the superalgebra whose maximal bosonic subalgebra is SU11, which captures the symmetries of SL2, and SU2, which captures the symmetries of the S3. And in terms of those fields, so one beta gamma system and two BC systems, you can obtain PSU112 level 1. And if you see here, I have written, I have 3 bosonic currents. So these, if you compute the commutation relations of these currents on the left, in terms of the OP that I gave you here, to do this exercise, you will find that they close into some SU11 level 1 algebra. And similarly for these 3, you will see that they close into some SU2 level 1 algebra. So here I find my ADS3 factor, and here I find my S3 factor. And then, okay, here I wanted to write also the supercharges. It's not important the precise expression, but you can check that the full supergroup can be built in terms of this portion here. So this captures our ADS3 cross S3. Okay. Then this portion here is our T4. And the last part you should think as ghosts. Okay, so this is the string theory we want to deform. It's unusual field content, but still they are free. So if we want to make computations, we can push them through. Okay. Questions? Okay. So in particular, something I should comment here. So here from this blackboard, all these expressions, it's not important you remember. The only one you should remember is that this J plus is just beta, so it's simple expression. And then this field gamma that I also introduced there should be thought as the boundary position coordinate. And this will turn out to be useful later. Particular now it's easy.
Angular coordinate?
So, for example, if in a when you are in position coordinate, I mean, your fields will depend on some variable, which indicates where you are in space-time.
Sure.
And this I'm claiming has a analog in the bulk, and is this field gamma.
Okay.
For example, if you compute this field gamma inside correlation functions, it localizes to the position coordinate of the spacetime theory. Okay, good. So from the way I presented things, and I'm selling this to you, it appears natural that whatever the bulk theory dual to this TT-bar deformed or is, it will be some deformation of this tensionless theory. But on the other hand, the trice is that this k equal to 1, you cannot work with the usual RNS formalism that people have been using for 30 years. So you have to rely on this hybrid formalism, which has a peculiar choice of ghosts, and which requires you to go to the superalgebra instead of just working with supersymmetry on the worldsheet. So why is this necessary? Can't we just analyze ADS3 cross S3 cross T4 with generic value of the tension, which is what people have been doing for a long time? Okay, so now let me try to address this point. So why this is not so bad? Why this is the easiest we can do? So, answer, why am I so obsessed and I'm insisting on the string theory being tensionless? Because I'm paying this price by having to rely on a new formalism, which I'm less used to. So the first point is that at generic tension, so I call K my tension. So if it's not minimal, the string theory, so ADS3, contains in the spectrum a continuum of states. So you can think of ADS3 at generic tension a bit as the hydrogen atom. So you have a continuum and then some discrete states. So ADS3 contains a continuum of states.
In the literature, though, we are used to discrete unitary representations almost all the time. In Causa-Klein literature, for example. Why suddenly are we talking continuous?
So
continuum?
You can, okay, there are two perspectives. So one thing you can do, you can study classical solutions of ADS3, okay? And what you find is that there are two classes. So if I draw my ADS3 space as a cylinder, you can have solutions that, so this is how time flows, that start very close to the boundary at past infinity. They shrink at time equals 0, and they again enlarge at plus infinity. And these, they are characterized by some radial momentum, which is a continuum parameter. Another way that you can see is if you study representation theory of SL2R, and you have the unitary representations with a spin, which is 1/2 plus IS with S any real number. Okay, so this is the continuum parameter, which in this picture is the
maybe this
continuous moment.
situation is special to ADS3 then.
I agree, yes.
In other words,
probably
in the literature, when you study Kaluza-Klein literature,
yes,
you have an ADS solution, let's say in 4 high dimensions. The spectrum around such a background is well understood and studied. It's always involving discrete unitary irreps. I never heard of.
Yeah, so this is a feature of ADS3 with pure SNS flux. As soon as you switch on some other flux, everything is discrete.
Okay, thank you.
So it's a special feature, I agree. But it's a feature we have to live with. So this means that the bulk theory contains a continuum of states only when the tension is bigger than 1, not in general. But this means that also the dual CFT must contain a continuum. Right? Otherwise, it can be the dual CFT. But if it contains a continuum, it means I cannot work with rational CFTs, right? So rational CFTs, by definition, are CFTs with finitely many representations. Here I have infinitely many. So this means that the CFT2 is not rational. And rational CFTs are usually the easiest to analyze, right? So our life is a little more complicated. Then, more in general, the exact CFT2 dual to ADS3 when the tension is not minimal is not a symmetric orbifold. Okay, this is by now understood. So it's not a symmetric orbifold. So even if we say, okay, maybe we can deal with the first line by having symmetric orbifold of some Liouville or some linear dilaton, something that introduces a continuum also in the boundary, is not even a symmetric orbifold. Okay? And more in general, we miss, again at k bigger than 1, we miss a first principle definition of the CFT2 dual to the ADS3 strings, dual to ADS3 strings. So in general, we don't even know precisely what the CFT2 is.
Why is that?
So, okay, what has been done for many years was computing, relating ADS3 cross S3 cross T4 strings, the symmetric orbifold of T4. But for a long time, people analyzed only protected quantities. By this, I mean that it doesn't matter where you are on the manifold of theories. So it doesn't matter the precise flux background. Now, more recently, it has been understood that in the case of pure NS-NS flux with just one NS5 brane in the background, this is what you mean by K. In this case, the duality becomes exact, and you can match all observables, not only the protected ones. Okay? But in general, we do not know what is the CFT which dares to manage everything. It does want to match protected observables. The symmetric orbifold is good anywhere, exactly because they are protected. But otherwise, we can match some observables. We can also match some special resonances where the worship travels all the way to the boundary, but not everything. Okay? So we do not know what the CFT2 is. We don't have a first principle definition for it that allows to compute and match any observable. So all these problems go away when we go to k equal 1. Because at k equal 1, the continuum of states is not there. So the dual CFT can be a rational CFT. And actually, it has been shown that the dual to ADS3 strings when the tension is minimal is indeed a symmetric orbifold, is what I was writing before. It's the symmetric orbifold of T4. So we do know the dual CFT2. After all, the least pain is staying tensionless and accepting this field content and working in this hybrid formalism, which is a new thing.
Berkovitz formalism.
Berkovitz, Bahawitian were the first author really advertising this formalism. Yes, it's that one.
And somehow going to Green-Schwarz formalism is no good, right? For this whole story is still based on NS.
Exactly, because I mean, all this relies on keeping manifest the CFT2 on the worksheet. Okay. And when you go to Green-Schwarz, you light congauge, and as soon as the light congauge, you do no longer see any worksheet CFT2. Okay, so in summary, we can say that ADS3 CFT2 at generic tension is already hard enough. Without any need to deform it. So if you want to deform a duality, better you understand the duality very well before you deform it. Okay. Okay, so good. I hope I convinced you that this is the least pain. At least I give you some motivation. But we're still with our question. So where do we start from if we want to replace that question? Okay, so what we did is to rely on what people did before us. And in particular, our starting point is a study at generic tension, indeed. It gives us the right direction. And so this is a paper by Gideon, Mitsaki, and Kutazov from 2017. And they show that the TTbar operator in the CFT2 is mapped in the bulk to a current operator is J plus, J bar plus. But remember, in our description of fields, this can be written as beta bar. And this is an operator in the bulk. And they showed this for bosonic ADS3 strings at A bigger than 1. Which we said is not ours. But what we did is, since we know the duality at k equal 1 very well, so our starting point inspired by this sequence of papers, we check that this correspondence still holds exactly for k equal 1, which have different formalisms, different rules, superstring, and no longer the bosonic string.
So on the one side, you have the exact marginal deformation. On the other side,
Indeed, yes. So, but this is not so counterintuitive, because we are saying that this TTbar operator, we can follow its fate for any value of the deformation. So in order for the string theory to also achieve that, it means that the string theory better be defined for any value of the coupling. But if you want that to be so, you need to deform by an exactly marginal operator. Okay, so yes, this is exactly marginal. This is irrelevant. Okay, so this means that in the duality that we had before, okay, so in place of the question mark, so we had here the symmetric orbifold of TTbar deformed T4, right? Many copies and then quotient by S. And we were asking, what should I write in place of the question mark? Well, J plus, beta beta bar, let me call deformation of the tensionless ADS3 cross S3 cross T4 string. Okay. This is, of course, not a proof. I'm just saying that the deformation operator I'm deforming by here, I know this operator in the undeformed theory. I can trace back, since I know the duality very well, to what it looks like in the string theory. And is on the worksheet is beta beta bar, which were two of my fancy collection of fields. So this is a good candidate.
Is there a reason why I should expect that the TTbar deformed theory could be described by string theory?
No, I mean, in general, we do not know how to. So given, this is an open question, right, in holography. If I give you a 2D CFT, can you tell me whether it is holographic? We don't know. We don't have a criterion to say which CFT are holographic, which not. We can start listing examples or listing some necessary properties, but we don't have a criterion. So it depends on your level of optimism. I don't think we have a precise criterion for that.
If you can verify this proposition, then you solve the problem, more or less.
Yes.
That's what it takes, right? This
Yes,
is sufficient.
But to solve the problem, which I would say to prove this double arrow, I would have to compute every possible observable here and match with every possible observable here, right? That means proving a DSCFT. Now, to convince that this is a good candidate, probably you need less. That's what I will do today. So I will convince you that one observable, meaning the one loop partition function, or the three-level in G-string spectrum, which is a non-protected observable, on the two sides is the same. Okay, so it's not a proof, but I think it's some non-trivial check that this is probably the best to be bet on candidate. Other questions? Okay, so let's go to the computational part. So don't be scared by these computations because we are doing free fields, okay? They are a bit strange because they're not just free bosons, this beta, gamma, and BC system, but they're still free. So the path integral can be done exactly. Okay, so
In general, what does it really mean to look for all observables being the same? It sounds like, is there a concise way of stating that goal?
so we can formulate the question in
There's some generating function or something.
Yeah, how do you prove that two theories are the same?
Yeah.
I would say that any experiment you do, you find the same results. So
where does it stop? I mean, it's endless, right? I mean, how
No,
do we
think
really
it's
know
endless.
all possible observables?
So, okay, you have the spectrum, you have correlation functions, maybe you have something like Wilson loops, but what else can you list?
So I have to compute all possible infinitely many correlation functions. That is just too much, right?
Yeah, I'm not saying it's easy, but for example, what has been done before the deformation is matching the spectrum at the whole non-perturbative spectrum at any genus, so any correction in the string. So that exhausts the spectrum. And then any correlation function in the large N limit. So at least at three-level in G-string, you can arbitrary endpoint functions have been matched. And the last step that remains is matching the higher genus correlation functions.
Okay.
So then what, you can ask for is some non-perturbative quantities or some kind of resurgence, but it's already pretty advanced as an understanding of a DSCFT, right? So we hope to get as close as we can with this deformed duality as was done for this capable one, which is close to a proof at this stage. Okay, so let's repeat our goal. Let's say once more is to compute string theory partition function. So string theory partition function, and we will compute these on locally ADS3 geometry with torus boundary. A is the one loop partition function, so it lives on a torus. Now, the action, in particular of this beta gamma system, you remember we had this beta gamma system was one of our fields. So since they are big fields, it's enough that you open Kolchinsky, and the action is just this. So it's beta TTbar gamma plus TTbar T gamma bar. So this is before the deformation. And we said we need to deform by beta beta bar. So I add lambda, which is my coupling, times beta beta bar. Right? So this will be the action. And the rest of the fields are unaffected. So all the rest of the list goes through. Now we want to compute these on local ADS3 geometry with torus boundary. And we have just three possibilities. So we have a list. So if I call H3 my global ADS3, I can find local ADS3 geometries with torus boundary as an orbifold. And this has torus boundaries in three cases. So I can quotient by a group Z. So this is what is usually called Euclidean or a thermal ADS3. Or a second possibility is to quotient by Z cross some Zm with M an integer, and this gives some conical singularities. Or the last option, which is the one we will consider, is quotienting by Z cross Z. And this is called the cut geometry. But this should be the most familiar to you, right? Is the notion that if I quotient the plane by identifying periodically lattice vectors, I obtain a torus. Okay? So we will consider in particular this. And this is the notion that the spacetime torus is obtained as a lattice of the plane. And in particular, we were saying that the spacetime coordinate, let me call it x, so this means that my x will be periodically identified by as x plus 1, okay? One side, one circle of the torus. And then on the other side will be identified with x plus t, where t is my modular parameter in spacetime. Okay. Now, we said that the spacetime position coordinate is mimicked in the bulk by this gamma field. So I copy the same relation, and the field gamma will have periodic boundary conditions that mimic this. And I will be more precise by what I mean by this field here. Okay, and our goal is computing the partition function. So let's just sketch its structure. So the structure is that, okay, it will depend on what? It depends on the space-time modular parameter. We already mentioned it here. And then being some string quantity, it also depends on the shape of the torus I have on the worldsheet modular parameter. The one I have to integrate over to label all the surfaces that enter my string field. And then, of course, it depends on the deformation parameter. Okay? And I can decompose this. Since I have free fields, this will factor into some beta gamma dependence. Okay? And this depends on all three parameters. And then I have the other list of fields that I mentioned. So the two BC systems and the T4 and the growth. But the good thing is that the only modification we did with respect to the undeformed theory is in this beta gamma system, because the deformation is that beta beta gamma, and all the others are free fields that commute with them. So these are unaffected. Okay, so this whole part we can copy from the undeformed string. And in particular, we can open those papers and see that these are given by 4 theta functions, essentially because these behave in Grassmann odd, they behave essentially as predeterminants. So this we just copy. And this is some array theta function, essentially the one coming from the momenta of the compact bosons. So this part is the easy part, just copy paste. And what we have to compute is just this beta gamma dependence. And we can compute it as a path integral. So it will be a sum over different boundary conditions, okay, which implement this. And for each boundary condition, it will be some path integral. So we have to integrate over gamma, its anti-holomorphic partner, gamma bar, over beta, the anti-holomorphic partner, beta bar. And then we have e to the minus the action. And this is for some special choice of boundary condition, which are a more precise formulation of these. And so it means that when gamma, you go once around the worldsheet torus, you get an integer times an integer many times t plus another integer many times 1. Okay, and the same for the other side. Okay, so this is the path integral we need to do. And the trick here is that, remember, the action is this one. And you see that there is no derivative for beta beta bar. So it's like an auxiliary field. So we can integrate it out. So the first step is integrate out beta beta bar. And this gives an action that after the integration, it just remains something that looks very close to two free bosons. Okay. And okay, this is the action. We have integrated out beta beta bar. And we can look at the classical equations of motion, right? So the equations of motion are d bar gamma equals 0. And we can solve these on the torus. And this says that gamma, which is a function of z and z bar, is some constant z plus some other constant z bar plus one last constant, okay? And this a and c, they can be fixed by imposing these relations, okay? So on these ansatz, I impose this, and I find a and b, sorry, a and c. So a turns out to be at plus b minus ct plus d. So the algebra may seem a bit tedious, but I just want to convince you that the computation that you can follow every step and it's not too far from the computation of the free boson, that partition function that you can find the yellow book of differentiation. Okay, so then I can replace these two into my action, right? So the action is d bar of gamma. So d bar of gamma, we select C. So we have something like integral of C modulus square. We integrate over the volume of the torus, which cancels this factor of tau 2. So what we are left with is sum over A, B, C, D. Then we integrate over the worldsheet, right? So over the modular parameter. Then we have the exponential, which was e to the minus s, and I just copy what I have there. Yes, we cannot create with this.
So the worldsheet is toroidal.
Yes, the worldsheet is a torus. But I have many tori, which is labeled by this. So I integrate over the fundamental domain. Okay. And then this is the beta gamma part, right? That we just computed, just added this integral. And then we copy the remaining parts that went along for the right, which were the S3 part, essentially. And we have the part from the theta functions. So we already recognize here that this is the partition function of 4 free fermions and 4 free bosons. So already here we start seeing something of where we should end up. Okay, so this is the partition function of the 4 torus, 4 free bosons, and 4 free fermions. And then the last step that we need to do is to go to some grand canonical ensemble, meaning that we sum over different values of capital N, which was the symmetric or the number of copies in the boundary, because formulae are more explicit in terms of this language. So if you go to some grand canonical ensemble, you can show that this can be rewritten in this shape. So first you trade the fundamental domain for the whole complex upper half plane. This is the last form, so we are done. Okay, you have some what I call the seed, and it depends on this modular parameter, and there is scaled lambda. Where the z seed I just defined, not to have too long expressions. Here I have an integral over the upper half planes. Then I have the exponential action. And then here I have my z of T4, which just stands for this. Okay, so this is then the result, that we succeeded or not. Meaning, can we spot the square root typical of TTbar here? So the first thing that we may recognize, if you go through the literature, is this first expression here. This is an old formula. Okay, I mean, you have to open the paper, of course. It's not that you remember by heart, but you can open And this is a famous paper from Digraph, Moore, Verlinde, which essentially they were given the recipe, given a 2D CFT, how you compute the partition function of each symmetric orbifold. And it's exactly this formula here. So given the partition function of some seed CFT, you can obtain the partition function of each symmetric orbifold by summing over all these integers. Okay, so this is the partition function of the symmetric orbifold. So this tells us that our string theory is dual to the symmetric orbifold of something. And this something, what this something is said in the second line. Now, also this formula appeared in the literature.
Sorry, what's the logic of going first line to the second line?
Okay, so the logic is the following. Usually, in the literature, for the symmetric orbifold, people don't write the partition function of the symmetric orbifold with n copies, but they write something like the partition function, they introduce some chemical potential, and the partition function of the orbifold with exactly n copies, and they sum over n. Okay. Now you can do the same in string theory if you couple to some background B field of the form sigma over 2 pi d gamma wedge d gamma bar. Okay, and this P here is 2 pi I sigma. So you introduce a chemical potential which accounts for the fact that the number of strings can fluctuate. Okay, so you go to some grand canonical picture. It's just a matter of convenience because formulas are much more easy to write in this fashion. And indeed, this Digraph Moore Verlinde formula takes this shape if you are in the grand canonical example. Just the choice of convenience. And so this is telling us, yes, you do have some symmetric orbifold. And this is telling us the symmetric orbifold of what? So essentially, this is also a formula which appeared in the TTbar literature, but let's pretend we didn't know. Okay, so what you can do is to write this as trace of q to the h0, q bar to the h0 bar, right? Where our q is just exponential of 2 pi I tau. Okay, then we have this integral over tau. Let's do it explicitly. There is some integral representation, or you can throw in Mathematica. It gives some closed expression. And what you find is that this you can write as the trace of, I don't want to call it q, because it's a different one. So exponential of 2 pi I t, and the same for t bar. So pi I minus I t bar. Sorry, let me write it better. So trace of exponential of 2 pi I t h lambda. Okay, so it's what you would call q if you didn't define already something that's called q, and 2 pi I t bar h lambda bar. And you can read what the dimensions are. And if you do this integral explicitly, which is just an exercise of throwing it in Mathematica, you find that h and h bar take exactly the form that was written before on the blackboard. So you will find a form for h lambda plus h lambda bar, which is the TTbar per root. So you will find, and all this can be done analytically, okay? So this first line is telling us, yes, you do have a symmetric orbifold of something. And the second line is telling us, do the integral explicitly, you will see of what the symmetric orbifold is, and is the TTbar deformation. So this is the role of the kernel of porphyry bosons and porphyry fermions.
Where does the tension enter this picture? Tensionlessness, that property, where?
From the very, very beginning. So the list of fields that I gave
Oh.
is only true, and the theory is only free
Mhm.
at K=1.
Okay.
Okay, so I have to restart everything if I don't. And I have this continuum, so I have to, and I need to have some guess for the boundary CFT2. So all the questions that I described so far.
So you never have to worry about world sheet action for a tensionless string, right? Because that's ill-defined, right?
Yes, I told you. So
Yeah.
the action I just need for this part, right? Only for the beta gamma.
That's harmless, that you can write down. Yes.
I can write down.
Normally, if somebody asks you to write down a string action for tensionless string, for zero tension, it's ill-defined, right?
Yeah, but here the tension is so okay.
Yeah.
We should distinguish the cartoon
By going
from the precise algebra.
By
So
going to hybrid formalism, you're able to write an action, even for tensionless case.
I agree.
But you didn't go to hybrid formalism.
I cannot.
It is defined, right?
It's ill-defined, exactly. That was the bottleneck for all these years, right? That at K=1, people didn't know, still I think don't know how to write the Vezzomino-Witten at level -1. Okay, so it is not known.
Although in this day and age of CFT technology, sometimes people tell you don't need a Lagrangian.
I agree.
But you have benefited from a Lagrangian.
Explored.
You've benefited from a Lagrangian.
Yes, here you do have a Lagrangian because it's a free theory, so you have everything you want in a free theory, essentially.
Okay, thank you.
Okay, so summarizing, yes, we get the same partition function. So this encourages us that what we propose to be the bulk theory dual to symmetric orbifold TTbar and deformed before is the right one. And what we are trying to explore now is, can we go beyond the spectrum? So can we understand correlation functions? For example, there is a debate in the literature of what should be the correct two-point function for TT-bar deformed theories. And there are different formulae. I can show you papers that claim that have different constructions and end up with different formulae.
Still not settled, two-point function?
But so the field theory is a bit peculiar. So for example, it's non-local. It doesn't have an it doesn't have a UV fixed point. So it's a bit peculiar. So
it's free field theory, you told us.
The string theory, the worship string theory is a free field theory. Okay.
Oh, okay.
Now, people analyzing from the boundary perspective have various difficulties to be challenged by. Okay. So the theory is non-local and it has some scale, you have some renormalization and all that. And so you can, now you have a string theory that should tell you not which is the correct description of TT-bar, but which is the holographic one. So in principle, from here, one could be able to define some BRST operator of the string and analyze which states are annihilated by the BRST operator. So this would give some vertex operators, which are physical operators to be matched with the boundary. Then you can go and compute correlation functions. And being the fields free, probably computations are doable. So this is what we are trying to explore now. Then in principle, you can look at asymptotic symmetries and ask, is the n=4 symmetry conserved or is it broken? You can ask, what is the group of asymptotic symmetries? Now it's no longer Virasoro. This we know because the conformal symmetry is broken, but what remains? So this is more or less the summary of the open questions, but please, I would like also to ask your questions and to listen to your comments. Thank you very much for your attention.
What is the paper where we can find all this wonderful wisdom?
Yes. So we have two papers. So one is this. And is by me, Knighton, and Naderi. And this is where we reformulate the tensionless ADS3 string in terms of this collection of fields. Before it was also described in terms of free fields, but you needed to take a coset, so the description was a bit more elaborate. In this paper, we show that this collection of fields is an equivalent and easier way to describe it. And then the whole thing on TT-bar and this computation which I sketched now which is a simplified version, is in this other paper where by, again, the same authors plus a subdepth set E. And there you can also find all the many references that I didn't mention because it's difficult on the Blackboard, but we are building on a literature exploring these dualities about TTbar deformations and deformations of ADS3 string theory.
If you consider for a moment the dual theory the field theory associated with M2 branes on ADS4 cross S7, presumably giving rise to ABJM model as a boundary field theory. Can one even dream the possibility of doing a membrane theory, fundamental membrane theory, to produce ABJM models? Well, analogous question.
Okay.
What you've dealt with today. Can it be addressed for ABJM model and
so essentially you're asking whether I can find some worksheet formulation.
or volume formulation?
Worksheet formulation for string theory that not only ADS3 but ADS4 or ADS5. Right.
No, I'm not asking for that. I'm really asking for membrane theory because ABJM model is supposed to be associated with M2 brane, right?
Correct.
Large number of coincident M2 branes. So therefore, they arise in M theory, in the dimensional M theory,
Yes.
not string theory.
Fine.
So
Yes, indeed.
why is it so difficult to imagine at least some problems to get started to do what you're doing for that case? But now you have to look for not a string worldsheet theory like you did,
Yes.
but a membrane theory.
Okay.
Is that, are you familiar with difficulties encountered in that? Or?
I'm not familiar with that. Yeah, I mean, the spot we are picking and the theories we are dealing with have many nice features, right?
Of course.
So this shouldn't give, there were students asking questions and they thought this is the average ADS-CFT. Usually ADS-CFT is much harder, right? So we are picking the dualities which are more tractable. That's why you can understand every single detail. And it will be harder in ADS5 or in ADS4 or in membrane theories.
Thank you.
So I think if there are more questions, you guys should talk with him in person. Let us thank the speaker again.
Thank you very much.
Very good. One of the best seminars I've heard.
Thank you.